Section: Introduction. In this section, we introduce text-to-image models that can create impressive images based on simple inputs like text prompts and sketches. These models are powerful for generating images and exploring creativity, but they often struggle to match exactly what users envision. This is because there is ambiguity in translating lower-dimensional inputs, such as text or sketches, into high-dimensional pixel space. For instance, the prompt, "a robot from the future," could lead to any number of robot images, similar to rolling dice, where different random seeds yield different results. Users often find it difficult to get a single image that captures all their desired elements. They might like one aspect of a robot from one image, another aspect from a different image, and yet another background from a third image. To address this, many approaches have been developed to give users more control, such as adding edges or depth maps. However, even with these added conditions, the process remains somewhat random, as users still receive a variety of outputs that can differ significantly. In our work, we propose a new method that allows users to create their desired image by combining parts from various generated images. We call this final result a generative photomontage, inspired by earlier work in interactive digital photomontage. Our approach enables users to first generate multiple images and then select the specific parts they want, giving them greater control over the final output. We start with a collection of images generated by ControlNet using the same text prompt and control inputs. Users can then choose their preferred parts from these images using simple brush strokes. Our key insight is that these images share similar structures, which we can utilize for composition. We introduce a technique that takes the user's brush strokes, segments the images in a special feature space, and then combines these segments during a final refinement process. Our method allows users to interactively select and blend regions from different images, enhancing both exploration and control. This is particularly useful when users may not know what they want until they see it. Additionally, users can replace unwanted areas with more appealing ones from other images, improving the overall result. Compared to the traditional trial and error method, our approach significantly increases the chances of success by allowing users to combine good regions from multiple images. We demonstrate our method's effectiveness across various applications, including creating new combinations, correcting misalignments, reducing artifacts, and improving alignment with prompts. Our approach outperforms existing methods in maintaining the realism and quality of local regions. In the related work section, we discuss how text-to-image generative models aim to learn real image distributions based on text inputs. Despite advancements in training techniques, these models often fail to produce the exact images users want in one attempt. Our goal is to bridge this gap by enabling users to compose their ideal images from multiple generated options. We also explore image editing capabilities, where text-to-image models allow for various editing tasks using reference images and text instructions. While many methods focus on adjusting the model's attention mechanisms, our approach differs by blending multiple images while preserving local details. Furthermore, we highlight the importance of controllable image generation, where enhancing user control through various input conditions is crucial. Unlike other methods that aim to create a single perfect image, we provide a complementary approach that allows users to select and combine elements from multiple images. Lastly, we draw inspiration from earlier works on image blending, particularly those using graph cut techniques. Our method optimizes in a feature space that captures more semantic information, making it better suited for compositing aligned image stacks while preserving user-selected regions. We also support multi-image segmentation with sparse user inputs. Section Summary. In this section, we introduce a novel approach to text-to-image generation that allows users to create a generative photomontage by compositing desired parts from multiple generated images, enhancing user control and satisfaction. Our method leverages user-selected regions and optimizes them in diffusion feature space, significantly improving the blending of images while preserving realism and fidelity. Section: Method. In this section, we describe our method, which takes a collection of generated images and creates a final image based on sparse user strokes. Our image stack is generated using ControlNet with one or more prompts. The images share similar structures because they are created from the same input conditions, like edge or depth maps. As users browse through the stack, they can select objects and areas by making broad strokes on the images. For instance, if a user wants to remove a rock from one image and add a red leaf from another, they would draw strokes on those specific elements. Our algorithm processes this user input and uses a multi-label graph cut optimization in feature space to segment the image regions across the stack while minimizing visible seams. We then apply a new injection method to blend these segmented regions during the denoising phase, resulting in a final composite image that integrates the user-selected areas while maintaining their local appearances. Next, we provide a brief overview of image space graph cut segmentation, followed by a detailed explanation of our feature-based multi-image segmentation and blending algorithms. In terms of segmentation, graph cut techniques are commonly used in various image tasks, including synthesis and analysis. We focus on multi-label graph cut in image space, where we have a stack of images labeled from 1 to n. Our goal is to assign a label to each pixel in the output image, ensuring that if a pixel is assigned a label, it matches the corresponding pixel in the selected image. The optimization process aims to find the best label assignments that minimize a defined energy cost function, which encourages seams to be placed in less noticeable areas. For our feature space graph cut, we utilize user strokes to find a segmentation that aligns with these strokes while minimizing seams. Unlike traditional methods, we perform the optimization in feature space, using key features from the self-attention layers of the diffusion model. These features provide a compact representation of the generated images, capturing rich appearance and semantic information, making them more effective for seam detection than raw pixel values. During the blending stage, we create composite self-attention features based on the label assignments, which are then used in ControlNet to produce the final image. We store the query, key, and value features of each image for all layers and time steps. After the user marks the desired regions, we conduct a multi-label graph cut using the stored key features from the first encoding layer. To ensure a good composite, we design our energy cost function to meet two criteria. It must respect user strokes and select inconspicuous seams for joining regions from different images. The energy function includes unary and pairwise costs. Unary costs penalize label assignments that do not match user strokes, while pairwise costs encourage seams to align with edges where neighboring features differ significantly. In summary, while individual image segmentation methods exist, they often lead to conflicts in overlapping objects across the image stack. Our multi-label graph cut optimization effectively addresses this by assigning unique labels to each location, streamlining the process. Section Summary. In this section, we describe our method that generates a final image from a stack of images based on user-defined strokes, utilizing multi-label graph cut optimization in feature space to minimize seams and ensure seamless blending of selected regions. Our approach leverages key features from a diffusion model to create natural composites while adhering to user input, avoiding conflicts that arise from individual image segmentation. Section. The above optimization gives us an image label assignment per feature location for the output image. We use this assignment to make composite features $Q text comp $K text comp and $V text comp from the respective features $Q, K, V of the image stack for each self-attention layer in ControlNet. We then inject these composite features $Q text comp $K text comp and $V text comp into ControlNet to form the final result. When users input strokes, they designate one image within the stack as the base image, usually the one whose background region is selected. During the blending stage, we use the seed and prompt of this base image when injecting the composite features. Specifically, we resize the label assignment map $L into the respective sizes of each self-attention layer $L. Then, we make composite features $Q text comp $K text comp $, and $V text comp $, as follows. Where $M_I_L$ is the binary mask of feature locations with the label assignment $I$, resized to layer $L$. $M_B$ represents the mask of the base image, where $B$ is the base image index. $Q_I_L$ are the query features $Q$ from image $I$ at layer $L$, stored during initial generation, and similarly for $K_I_L$ and $V_L$. $Q text model are the query features generated from the model during the blending stage, which are different from those during the initial generation. These composite features are injected into the UNet's self-attention maps for all layers and time steps. Note that we inject the initially generated self-attention features for all images except for $Q_B$, the query features of the base image. If we inject the initial $Q_B$ features, we often observe suboptimal blending at the seams. As noted in previous literature, $Q$ influences the image structure, while $K$ and $V$ influence the appearance. Hence, injecting $Q_B$ and thus completely overriding the $Q$ features eliminates the opportunity for the model to adapt the image structure near the seams. Allowing $Q$ within the mask $M_B$ to change over time allows the model to adapt to the different graph cut regions when blending, Figure A. It also adjusts the low-resolution graph cut boundaries to align with semantic features in high-resolution pixel space, Figure B. In this section, we describe how we optimize image label assignments for each feature location in the output image. We use these assignments to create composite features, specifically, query, key, and value features, from the original features of the image stack for each self-attention layer in ControlNet. We then inject these composite features into ControlNet to produce the final output. When users provide strokes, they select one image from the stack as the base image, typically the one with the chosen background. During the blending process, we utilize the seed and prompt from this base image. We resize the label assignment map to match the sizes of each self-attention layer. The composite features are formed using binary masks that indicate feature locations based on the label assignments. We ensure that the initially generated self-attention features are injected for all images except for the query features of the base image. If we were to use the base image's initial query features, we often see poor blending at the edges. This is because the query features shape the image structure, while the key and value features affect the appearance. By allowing the query features within the base image mask to change over time, we enable the model to adapt to different regions during blending, aligning low-resolution boundaries with high-resolution semantic features. Our method enhances the ability to combine generated images, giving users more flexibility and control. We present various use cases and showcase impressive results from different pre-trained ControlNet models with Stable Diffusion 1.5, including Canny Edge, ScribbleMap, OpenPose, and DepthMap. In terms of appearance mixing, we demonstrate applications in creative design, where users refine images based on their preferences. This is particularly useful for users who may not know what they want until they see it. For instance, users can explore architectural designs by merging elements like roofs and windows from different images or adding unique features to create something new. Regarding shape and artifact correction, our method allows users to adjust object shapes and scene layouts when ControlNet struggles to meet their input conditions, especially for uncommon shapes. For example, if a user wants to create a rock shape like an Apple logo, they can replace parts of the image with patches from other images in the stack to achieve the desired result. Additionally, our method improves prompt alignment when the generated output does not accurately reflect the input prompt. Users can simplify complex prompts and selectively combine outputs to create the desired image. We recommend using our method alongside existing techniques for enhanced accuracy and control. Section Summary. In this section, we describe how we optimize image label assignments to create composite features for self-attention layers in ControlNet, allowing for flexible blending of images based on user input. Our method enhances creative design, shape correction, and prompt alignment, enabling users to achieve desired results by combining and refining generated images. Section: Evaluation. In this section, we evaluate our method's performance. Our graph cut process takes about 1 second, while the blending stage requires approximately 7 to 13 seconds on an NVIDIA A6000 GPU for 2 to 5 images, with sizes ranging from 512 by 512 to 1024 by 512 pixels. For comparison, a single forward pass of vanilla ControlNet takes between 7 and 17 seconds for a batch of 5 images. The storage needed for the initially generated QKV features varies with image resolution, averaging around 2 GB for a 512 by 512 image. To reduce storage, we can keep only a subset of features, which may lower appearance quality. More details can be found in the appendix. Next, we compare our method against several baselines using examples from various use cases. For segmentation, we assess our multi-label graph cut against a modified version of SAM and the pixel space graph cut from Interactive Digital Photomontage. SAM is designed for single images, making it challenging to adapt for multiple images without overlaps. In our baseline setup, we run SAM on each image in a stack, using user strokes as positive and negative samples. SAM produces pixel-wise logits, and we assign labels based on the highest logit score. However, we observe two main issues: noisy labels within objects and segmentation that does not align with user strokes. For the interactive digital photomontage comparison, we use their pixel space graph cut with a seam objective based on a Sobel filter applied to RGB values. We find that this method can be sensitive to minor color changes, leading to undesirable seam selections. In contrast, our diffusion feature-based graph cut aligns seams more closely with semantic features and operates more efficiently due to lower resolution diffusion features. In blending, we focus on overall realism and local fidelity in user-selected areas. We qualitatively compare our results with several baselines. The interactive digital photomontage uses Poisson blending, which can alter colors due to wide variations in generated images. Our method better preserves local color and appearance. The blended latent diffusion method combines noise from multiple images, but this can lead to changes in the base image's appearance and introduce artifacts. We also explore fusing noises with greater overlap, inspired by multi-diffusion, but this results in more seam artifacts. We compare our method with an adapted version of MASA CTRL using ControlNet, where we designate the base image as the target and the others as sources. This adaptation can also alter the base image's appearance and introduce blending artifacts. We further compare against other diffusion-based methods like collage diffusion and cross-domain compositing, which struggle to maintain local appearance during blending. We also assess GP-GAN and deep image blending, which show artifacts in blended areas. More qualitative results and additional baselines are available in the appendix. For quantitative metrics, we calculate local appearance fidelity using masked LPIPS and PSNR. We resize the masks from our graph cut to match image dimensions for LPIPS and compare blended results with image space composites for PSNR. The image space composites contain noticeable seams and serve as a proxy due to the lack of ground truth data. We also compute the seam gradient score to measure seam artifacts, expecting some seams to fall on object boundaries. We report the minimum, average, and maximum seam gradient scores for each image stack in a table. Our quantitative results indicate that our method achieves the highest PSNR score and the second lowest LPIPS loss among all baselines. Our seam gradient score is within the expected range and close to the average score. Collage diffusion shows a high seam gradient score due to significant seam artifacts, while GP-GAN has a low score because of faded images with reduced color range. Deep image blending and cross-domain compositing exhibit relatively high LPIPS losses, and blended latent diffusion ranks second in PSNR, outperforming its variant. Finally, we conduct 2 user surveys to compare our results with the most competitive baselines in each domain: interactive digital photomontage, blended latent diffusion, and MASA CTRL with ControlNet. Participants select the most realistic image and the best at blending selected regions. Our findings show that our method is comparable to MASA CTRL in realism but significantly outperforms the baselines in blending quality. Section Summary. In this section, we evaluate our graph cut method and blending stage, which run efficiently on an NVIDIA A6000 GPU, and compare it against various baselines, demonstrating superior local appearance fidelity and blending quality. Our quantitative results indicate that our method achieves the highest PSNR score and performs well in user surveys, highlighting its effectiveness in realistic image blending. Section: Ablation Study. In this section, we conduct an ablation study of our self-attention injection method by comparing it with other injection strategies tailored to our specific needs. We use the same graph cut segmentation as input for these comparisons. First, we explore the use of shared key and value features, which combine multiple features into one set, similar to what Hertz et al. Did for transferring styles between images. The results, shown in the accompanying figure, reveal that these alternative strategies can alter local image details, such as the background of a dog, the head of a robot, the color of a snake, and the appearance of a waffle. Our findings support the idea that the query features affect the overall image structure, while the key and value features impact the image's appearance. By using combined key and value features, we allow the query features to connect with keys from outside the target image area, leading to changes in appearance. In contrast, our method restricts access to keys and values from only the target image region, helping to maintain local appearances. Next, we examine the use of model-specific key and value features for the base image, which also allows for changes in appearance. By incorporating the base image's stored key and value features during the initial generation, we can preserve its appearance during blending. For further details on graph cut features and attention injection parameters, we refer to the appendix. In our discussion, we present our new image generation approach, which involves combining multiple images generated by ControlNet. We introduce a method for segmenting and blending these images using their diffusion features, demonstrating various practical applications. More broadly, our work suggests a new way for users to interact with text-to-image models. Instead of aiming for a single final image, users can treat the model's outputs as intermediate steps, allowing for more precise control over the final result and maximizing the model's generative potential. However, we acknowledge some limitations in our method. Our current graph cut parameters are chosen to promote coherent regions, which can sometimes lead to less precise boundaries, especially for objects with curvy outlines. While this approach works well in many situations, it may require users to make additional adjustments. Since the graph cut process is nearly real-time, users can quickly visualize the results and make necessary iterations. Additionally, our method assumes some level of spatial consistency among the images in the stack. If the images vary significantly in structure, users may need to select appropriate regions to create a valid scene. Users can enhance spatial consistency by providing more structured input. Future research could explore ways to ease these spatial consistency requirements and automatically adapt to significant changes in scene structure during segmentation and blending. We would like to express our gratitude to Kangol Deng for assisting with the user survey setup. We also appreciate the valuable feedback from Maxwell Jones, Gaurav Parmar, and Shengyu Wang, as well as initial discussions with Potoshnik. This project has received partial support from the Amazon Faculty Research Award, DARPA École, the Packard Fellowship, and a joint NSF-CISF research grant.